Good morning, Emil. Thank you very much for the opportunity to show our project on cap ceilings, which is very much related, but I want to start by probably bringing this a bit to the context of BOL, because when let's say, started with this project like 1.5 years ago, I had actually no idea where this was going, and it's always evolving and something happens. And I think we're all very grateful that we got this opportunity, thank you, and to just come here and have a very supporting environment that enables us to go forward with this, because this is not a very planned process. It started actually with an architectural design thesis, like a studio project, of which we see a render here. And the underlying question was, how can we actually go on building things like a high rise, for instance, but of course, as you all know, there is a lot going on with all timber and mass timber construction, and we tried to look into a different way and look more into historic building elements and building types. The project was here in Siemensstadt, which, as you probably know, is a very masonry-like district, and we looked at these historic build-ups of these masonry structures, especially of the Schaltwerk Hochhaus, which is a very efficient construction, as we found out in an LCA analysis that we did of this historic thing. And then we thought, how can we bring this back, what they did like 100 years ago, to a modern construction environment and actually continue building in a more sustainable way. So you also have seen this graph already in Zakib's presentation, and what we see here is an LCA analysis or comparison study between different ceiling types. And why are we looking at ceilings? Again, ceilings have the most mass in a building. So if we want to reduce carbon, mass is very important. So we compared these things, and of course, like the most common thing in construction today is this flat reinforced concrete slabs, and then we compared again to these timber constructions also, and we found out that these historic cap ceilings, which are vaulted structures, are actually do actually have even less embodied carbon than these timber build-ups. And why is that? Because on the one hand, of course, your slab structure needs to be able to support the lasten, like the loads, of course, but that's only a small part, and one even more important part due to regulation, especially in a more developed context, is sound insulation. So mass also equals, the more mass you have, the more sound insulation you have. And that's why buildings are becoming heavier and heavier as regulation on sound insulation is going up. And that's a problem of timber construction, because timber, of course, is very light. So what you do in the end is you pour, again, concrete on top to make it heavier. And that is probably not such a good idea in this regard. And the great thing now about the cap ceiling, as it is made of masonry, is that we have a significant mass, but it's not concrete. And you can also bring, again, mass on top in form of like some kind of heavy material, like gravel or something, to go or to meet these sound insulation requirements. So we also published these comparison studies quite recently in journal article, and that's one thing we thought. The question was, like, we found out it could be a good idea to build cap ceilings, but what does it take? And another important part, of course, that is going on is the circularity of structures. So the possibility to take things apart again at the end of a life cycle. And in this regard, also, this structure is quite well fitted for this, because each component has a very specific task in the whole system. So as it is vaulted, the structure is purely compression loaded, as opposing in a reinforced structure where you have tension and compression in the system. So in this case, we can separate these two things. We can put some tension anchors into the system that you can screw out in the end, and you have the compression loaded masonry, which you can take out in the end. And yeah, it's all a very modular setup. So we tried to make, in the end, three transformations to the whole system to propose a buildable structure again of these cap ceilings. And these three transformations were, one, we also tried to implement these acoustic properties that Sakib is researching in his additive manufacturing project in the scale of a brick. The second one is we tried to substitute the beams, which are in a historic type, usually steel, by modern timber beams. And the third transformation being that we try to fabricate this all in a modern way. So the first one, the acoustic transformation, is that we try to bring these Helmholtz-Resonatoren to the scale of a brick. So this is again the principle of these Helmholtz-Resonatoren, which are these bottle-like structures that we want to bring into the brick. These were the first prototypes. And the interesting thing, I think, here also about the research is that the whole idea, of course, comes from this possibility of additive manufacturing, as shown in your project. But in this case, probably makes just much more sense to fabricate it in a traditional way, because you have like a certain amount of different types, and then you can just cast them and produce them in a mass amount. And but I think this process is quite interesting, that you need to have this starting point of thought that comes from definitely the additive manufacturing, and then again you bring it back to this way of traditional fabrication, which is the next stage for this project. Just yesterday, we filed to, we're working on this with a brick manufacturing company from Brandenburg, which is going to produce these bricks for us that we then can test. A second transformation being the digital fabrication. This is also the picture you have seen already also in the presentation, and the picture that has been hanging here around. And we were very grateful that we had the opportunity to use the BOL robot to try a first prototype of how a modern production environment for these cap ceilings could look. Basic idea being you have a robot that can just place the bricks into this shape and do this in a industrialized fashion. So the whole system is running on rails and is actually quite fast in building these cap ceiling structures as a prefab element. So the prototype that you can also see in the MMD lab that is standing there, the pure building time of it is 24 minutes. So we did it in 2 runs. Each run was 12 minutes. Quite for a first try, quite competitive time for building these things in a robotic way. And then the third and last transformations is to substitute the historic steel beams with a modern timber beam, making the overall life cycle assessment even better for the whole system. And the great thing about timber, of course, is that you can shape it in a way that fits the system very great. So we developed this cross section that works quite well with the cap ceiling itself, because it has this angle in the timber. And we had a great chance to build this as a demonstrator that we were not able to keep, unfortunately, last summer in Aachen at the Zukunftsbau pop-up campus. And we compared also there. We did it by hand with a master mason who also showed us a lot that we didn't know, knowledge that you can get from books about how to really make a great vault. And we built it all by recycled bricks that came also from the region there. Yes, and there's some pictures from the process, which Yeah, it's always quite dirty. That's a bit of a contradiction that we also experienced there in the MMD lab. We have to, if you build with mortar and stuff, it's not probably the best environment to go with the delicate robots and delicate technology. But yeah, I think we managed to find a good balance between that. And if you are interested, you have the possibility to scan this QR code and see the whole video documentation about the project. Thank you.